In the last video, I talked about the inverse relationship between frequency and period. If you think about those two equations, the period would be equal to the inverse, 1 over frequency, and the frequency would be equal to 1 over the period. In this video, I'm going to talk about wavelength, velocity, and do an example problem. Okay. Wavelength is kind of what the word says. It's the length of a single wave, the length of one wave. Okay, it's a distance, so it's measured in meters, centimeters, feet. Any distance measurement you can use for wavelength. Okay, the symbol that it's designated is lambda, the Greek letter lambda. Looks like kind of upside down y on the back of your equation sheet. Forget. So the length of one wave. Well, if we have distance, and what we learned last semester was that velocity is equal to distance over time, right? Distance over time, or d over t. And so here we can think about frequency would be the number of waves per second. Period would be thought about at time, right? Because it's a unit of seconds. Okay, so we can think about this as the velocity would be equal to the wavelength divided by the period. That would also give us velocity. Okay, but because velocity and period are inverse of one another, right? So if this is our equation, if we substitute for p 1 over f, right, this would be p is equal to 1 over frequency, right? That means that if you cancel this out, take the reciprocal of this, right? That's going to flip the frequency on the top and divide it by 1. So that means that the velocity is equal to the wavelength times the frequency. Okay, because the inverse of each other. All right. Period, frequency, inverses of each other, which means that wavelength and frequency are inverse of each other. Wavelength and period are directly related to each other. Okay, so you can think about that for those questions in the problems. But here's an example that I'd like to use using these concepts, this idea, similar to number 9 on the worksheet that I gave you. So here we have Conscious Lake. There are 2 docks, and they are 34 meters apart. Pictures are worth 1,000 words. I'm going to draw my 2 docks. Okay, crest at each dock. So there's a crest here. Here, let's make my water blue. I like blue water. So there's a crest at this dock. Okay, there's another crest at this dock, and we have 5 crests in between those two. So 1, 2, 3, 4, 5 crests there. Okay, and so if we measured the distance between these 2 docks, here to here, would be 34 meters. 34 meters, and what we'd have is we'd have 1 repetition, 2, 3, 4, 5, 6. So we have 6 waves. You think about this as standing wave, but because there's 1, 2, 3, 4, 5, 6, 7 total crests. That's 6 complete repetitions. Okay, and so if we would be the drawing here. Okay, if we want to know the wavelength, right? The wavelength is equal to the length of one wave. Okay, so we have the length on top. We have the length divided by the number of waves. Think about it. Okay, and so we have the length of 34 meters right on the top, and we have 1, 2, 3, 4, 5, 6 total waves. Okay, so our wavelength, the length of one wave, because you have 6, would be 34 divided by 6. Take out your trusty calculator there. I'll move this so you can see it. So this would be 34 divided by 6. I believe this. Yeah, 34 divided by 6. It's going to give us a wavelength of 5.67. So the wavelength is equal to 5.67 meters. Okay, so there's our wavelength. Next it says if 20 waves pass one dock every 12.5 seconds. Okay, so that would be number of waves equals 20, and the time is equal to 12.5 seconds, right? And we're trying to find the period and the frequency. Okay, remember the frequency is the number of waves take place each second. So if we put number of waves divided by the time, 20 waves divided by the 12.5 seconds, right? So this would be per seconds, right? 20 divided by 12.5, not 15.5, 12. Just fix that real quick. Mistakes. 12.5 seconds. So 20 divided by 12.5 gives us a wavelength, a frequency of 1.6 hertz. 1.6 hertz. Okay. Period, of course, is the time for one wave to go by. Okay, so the time it takes for one wave to go by. So that means we want the time divided by the waves. So for period, it's going to be 12, time on top, 12.5 seconds, divided by 20 waves. It's going to give us 12.5 divided by 20, because it's 0.63. Period would be equal to 0.63 seconds. So it takes 0.63 seconds for one wave to go by. It takes 1.6 waves go by every second, which hopefully makes sense. Another way you could do this is by taking the reciprocal, the inverse of the frequency. So if we took 1 divided by 1.6, if you notice, 1 divided by 1.6, the reciprocal, gives us the exact same answer. Don't you love math? It's a beautiful thing. Last thing is the speed. And so if we look at this equation, the speed is either distance divided by time, so wavelength divided by period, or you can do it as frequency times wavelength. Either one will work. Try both just to test it. Okay, and so if we take our wavelength as 5.67 meters, take our frequency 1.6 hertz. Okay, we take velocity is equal to wavelength times frequency. It's going to be 5.67 meters times 1.6. Nicer. 1.6 hertz, which is also would be per seconds, right? So giving us meters per second. Okay. And we'd have a speed of 5.67 times 1.6 equals a speed of say 3 significant digits here, 9.07 meters per second. You could also try wavelength divided by the period. It'll give you the same answer. Okay. So think about those concepts, see if you can apply them to those problems. Try them on your own. Let me know if you have any questions. Good luck.